Okay. Refraction. So far, we have learned about a reflection, absorption, and we know what the absorption means. It means that when the light, which we are studying a visible light here, if visible light is blocked or by a material, it can be opaque material, and that opaque material absorbs the light and it doesn't let the light pass or be reflected. Okay, so and that's why we call absorbing light or absorption. Then we will have a reflection. What does it mean if we have a material that reflects the light? So we will have a reflection of the light. And we discussed about the reflection, the law of reflection, the angle of incidence. It will be always equal to the angle of reflection. What is the angle of incidence? The angle between the normal line and the incident ray or incident visible light is called angle of incident, and the angle of reflection, again the angle between the normal line and the angle of and the reflected ray will be the angle of reflection. So based on the law of reflection, for visible light the angle of incidence is equal to the angle of reflection. By using this law, we would be able to see the image of object in front of the plane mirror, concave mirror, and convex mirror. Good? So by just using this law. Today, we will be discussing about the refraction, what the refraction is. So we already know that the velocity of light in the vacuum is 300 million meter per second, or 3 times 10 to the power of 8 meter per second. Good? So when the light or visible light travel from one medium to another medium, what happens? The velocity of the visible light will change. Whenever the velocity of light changes, we will have refraction. That's it. So the velocity of light, whenever the velocity of light change, light will be refracted. Instead of traveling through the straight line, the light will bend. You remember when we were calculating the sound or talking about the velocity of the sound? We would say the velocity of sound would change as the temperature increases. When the temperature increases, medium is changing, yes? Here we will have the same thing. If light travel from one medium to another medium, its velocity change, instead of moving through the straight line, we know that the light travel through the straight line, yes? Instead of traveling through this straight line, it will bend. So this is called refraction. For instance, in this example, so right now we have a light source. Let's say this is a light source, okay? And the light is in the air, okay? Visible light. And the velocity of the visible light in the air is almost equal to the velocity of light in the vacuum. It is 3 times 10 to the power of 8 meter per second. What exactly happened here? The light, nothing happened to the light here. Good. But when the light reach here, we are expecting the light travel through this straight line, yes? We are expecting the light travel through this straight line. It doesn't travel. Why? Because the velocity of light is changed. when the velocity of light is changed, we will have refraction. The light will bend. So you may say the light bend this way or that way, okay? Because both are bending. This way or that way. That's why we define a normal line. What is the normal line? Normal line is a virtual line which is always perpendicular to the surface that the light is passing. Good? So this is a normal line. I call it N. Okay? And it is a dashed line which is always perpendicular to the surface. What is the surface here? Two medium. Yes? Air and water. Okay? So based on this, okay, I can say, okay, now I would be able to say that when the light is bending toward to the normal line or away from normal line. Rule number one, whenever the light or visible light is traveling from a medium to another medium, when the velocity of light decrease, the light bend toward to the normal line. The velocity of light in the air is 3 times 10 to the power of 8 meter per second, yes? When the light move toward to the, when the light enter to the water, its velocity decrease. When its velocity decrease, that's why this light, instead of traveling through this straight line, see, instead of traveling through this straight line, it bends toward to the normal line. Okay. Example. What happens if we have, so I can say now I have now water and then air. We have an incident light, good, and this is a normal line. Yep. The light, we have a light source, okay? The light source is in the water, and the light is moving from a water to air. What happened to the velocity of light? Increase or decrease? Increase. When the light moving from water to the air, its velocity increase. Or we can say when the light is moving from high refractive index to the low refractive index, the its velocity increase. We will talk about the refractive index, okay? Each material that can pass the light through itself, it does have a refractive index. Okay? So, because we already know that what happened, the velocity, we are expecting the light go through this straight line, yes? If there was no medium, the light goes through the straight line. But there is a medium, the medium is air, the velocity of light increase. When the velocity of light increase, the bending light will move away from the normal line. What would be the refracted light? This is going to be the refracted. So whenever the velocity of when light travel from medium number 1 to medium number 2, if the velocity increase, the refracted light bend away from the normal line, when the visible light which traveling from medium number 1 to medium number 2, if its velocity decrease, it bend toward to the normal. That's all that we discussed today. So again, like the reflection, I call this angle of incident. What is the angle of incident? The angle between the normal line and the incident ray. And then I call these the angle of reflection. Good. What is the angle of refraction? What is the angle of refraction? The angle between the normal line and the refracted light. If velocity increase, theta r is bigger than theta I. Good. If velocity decrease, good, what happened? The angle of incident is going to be bigger than the angle of refraction. Yes? So the angle of refraction is going to be smaller than angle of incident. Good? So this is the law of refraction. The velocity of light, visible light, change, increase or decrease. If the velocity of light increase, the refracted light bend away from the normal line. That's why the angle of refraction is going to be bigger than the angle of incident. Good. If the velocity of light or ray decrease, the angle of refraction will be smaller than the angle of incident. It means that the refracted light bend toward to the normal line. That's it. Any question? Does this make sense? Yes? This is all that we will study today. Okay? So, but as you remember, I said we have a refractive index. So water has its own refractive index, is the quality of the water. It says that how much the velocity of water, light, it change. Let's say you have a glass, you have a water, okay? You have a cup of coffee, and then you have a, canola oil. You would like to pass the light through each medium: air, water, cup of coffee, and oil. The density of each material is different. Yes? The volume density of each material is different. So the oil is more dense than water. Coffee is more dense than air. Yes? So definitely the light which pass through each medium will have different velocity. I can say that the velocity of light when it's passing through the oil, okay, it's going to be, smaller than when it's passing from the water. Good? Because it's absorbed with more dense material. Okay, so how we can just differentiate the velocity of light on each medium? That's why we define the refractive index. So what is the refractive index? Okay, I'll just explain right now. And we just show the refractive index of any material, any medium, N medium. And this medium can be air, can be water, can be glass, oil, anything. that can pass the visible light. N is equal to C. What is the C? Velocity of light. Velocity of light divided by V. What is the V? Velocity of light on the medium. Good. Velocity of light on the medium. We know that the velocity of light in the air is different than velocity of light in the water is different than velocity of light in the oil. So when we divide this number, the velocity of light, to the velocity of light on that medium, we would be able to calculate the refractive index. So, question, N of vacuum. What is the N of vacuum? Who can say? Go ahead. No, N of the vacuum. Okay, what is the value of the vacuum? How we can calculate the N of the refractive index of vacuum? Is 1. Why? The speed of light in the vacuum. The speed of light in the vacuum is the C, yes? So, see here, C divided by, C divided by velocity of light in the vacuum. We already know that the velocity of light in the vacuum is exactly the velocity of light. Nothing happened. Good? The light doesn't bend. So what is going to be this? 1. But N of water is going to be what? C divided by velocity of light in the water. What is this value? Is going to be bigger than 1 or less than 1? Bigger than 1. Because C divided by velocity of water, or velocity of light in the water. Velocity of light in the water is smaller than the velocity of light in the vacuum, or the velocity of light. That's why this value is going to be bigger than 1. We can calculate N of the glass, any glass, okay, with different thickness. So again, C, the velocity of light divided by the velocity of light in the glass. Again, it's bigger than 1, but N of water and N of glass will be different. Because we know that the velocity of glass is, the light in the glass is different than the velocity of the light in the water. Good, good. The one that has more velocity will have less refractive index, yes? Okay. So let me just show you a refractive index for different if so again, see, this is the formula. N of material is the velocity of light divided by the velocity of light on that material. Okay, if you have the velocity of light in any material, you would be able to calculate the refractive index of on that material or that medium. Water, air, oil, anything, coffee, whatever. So this table shows the vacuum, refractive index or index of refraction is for vacuum is 1. And it makes sense. For air, it is 1.0003, is almost equal to 1. Okay, if you round it to 1 decimal or 3 decimal places, yes, it's going to be almost 1. Good. So ice 1.31, water 1.33, and plexiglass, okay, 1.5. The more dense the medium get, yes, the higher refractive index, okay, or the index of refraction we will have. Good. Diamond is 2.4. And then what we have, yes, okay, there are, we will have other material as well, okay? So, let's say we have light is moving from ice to the water. What happened? From ice to the water. Can you think about that? Let's say we have, let me just show here. What is the index of refraction for ice? 1.31. And what is the refractive index for water? 1.33. Yes? Okay, let me just write it down here. Ice is close. Ice 1.31, and of water is 1.33, and the light is traveling from ice to water. And let's say this is a normal line. Good. And then this is the angle of incidence, yes? So what happened to the refracted light? So let me just insert image upload. Oh, what happened? It's gone? Okay, let me just draw one more time. So we have ice. What was that? 1.31, yes? And a water is 1.33. And then we have light which move from ice to water. Good. And let's say the angle of incidence, this theta I, is 30 degree. Good. What happened to the angle of refraction? Okay, you just say it's going to be bigger than 30 degree or going to be smaller than 30 degree. Good. And then you can just participate to the class. Okay, so just go and again go to the classpoint.app and put this class code and or scan this. You can discuss together. Yeah. You can refresh or completely. Passcode is 55278. Yes.
You got it? No.
Is there what's the error? Oops, there is an error.
I put it in the class code correctly. Is anyone else getting in?
I got it, but it was just good screen.
Stream's not finished loading.
Is not loading up.
That's like stuck recorded.
You don't see this page?
The loading bar that's on the bottom is stuck in a quarter.
Okay, let me just.
So I mean,
So you cannot upload anything, yes? Can you upload anything? No. Okay, let me just see what's the issue. Let me just change the class. Start a new class. Okay, try this one. Okay, so now the class code is 31174.
and the phone's not going too well. Yeah.
Same thing? Okay, that's okay. Okay, just write in a piece of paper. Okay, I will come and check your answer. Good? So let me just. Again, N of ice, I will write one more time, 1.31. N of water, it was 1.33. So the light is traveling from ice to water, and this is a normal line. And the angle of incidence, let's say theta I is 30 degree. What happened to the angle of, okay, what is the angle of refraction? Okay, I don't want to calculate the value. Just say it is bigger than 30 degree or theta r less than 30 degree. Which one? And you should know that the n of medium, yes, is equal to c divided by the velocity of that the light on that medium. Good. This is the formula of the index of refraction.
So the reverse,
Hmm?
the reverse N and the B are.
Yes. Perfect.
It's N number slower this.
And refractive index and the velocity, okay, are inversely related to each other. So if you see high refractive index, good, the velocity of light on that material is less. Okay? High refractive index, the velocity is less. Good? Less refractive index. Okay, when you compare the refractive index, okay, the one has a bigger refractive index will have less velocity. Good? 1 more minute or 2 minutes. 2 minutes. You just need to say, okay, the angle of refraction is going to be bigger than 30 degree or less than 30 degree. And the light is traveling from ice to water. The index of refraction for in ice, the refractive index of ice is smaller than the refractive index of water. So it means that the velocity of light in the ice is bigger than the velocity of the light in water, yes? Vice versa. The one has a smaller, good. Refractive index, okay, will have a bigger velocity. Again, if you place this number here, so you would be able, or you can just write down like this, okay? If I want to find out the velocity of medium, the velocity of light and the medium is going to be c divided by n of that medium. Good? Algebraic. Right now, is bigger or smaller? Are you done or are you still need time to think? Done? Okay, good. So how many of you say the angle of refraction is bigger than 30 degree? How many of you say the angle of refraction is less than 30 degree? Okay. See, I just want to explain with the formula first, and then I will explain conceptually, okay, what exactly happened. So let's say we have, again, this formula, velocity. Let me just change the color. The velocity of light in the eyes is going to be what? 3 times 10 to the power of 8 meter per second. What is the refractive index in the eyes? 1.31. Good. And then velocity of light in water is going to be what? 3 times 10 to the power of 8 meter per second divided by 1.33. Okay. Good. So when you calculate this, do you have a calculator? Let me just calculate this. 3 divided by 1.31 is going to be 2.29, yes? 2.29 times 10 to the power of 8 meter per second. And then 3 divided by 1.33 is going to be 2.25 10 to the power of 8 meter per second. Okay. The velocity of light in the ice, is 2.29, good, times 10 to the power of 8 meter per second. The velocity of light in the water is going to be what? 2.25 10 to the power of 8 meter per second. The light is going from ice to the water. What happened to the velocity? It's smaller. When the velocity gets smaller, bend toward to the normal line. Yes? When the velocity of light decrease, the refracted light bend toward to the normal line. So instead of traveling, instead of traveling to the straight line, yes, it's bend toward to the normal line. Good. So this is going to be the angle of refraction. So the angle of refraction, which one is the correct answer? This one is the correct. Okay. So what does it mean? If the light is traveling from the less refractive index to the high refractive index, the velocity of light decreases. When the light is traveling from high refractive index to the less refractive index, the velocity of light increase. Good? And we know that what happened if the velocity increase, the refracted light bend away. If the velocity decrease, refracted light bends toward to the normal line. Any question? Is it clear? Good? Okay. The rest that we will study here is the application of refraction. So that's why we just try to learn about lenses. So we have a concave lenses and convex lenses, and also the prism. What is the prism? The prism is a kind of triangle glass that pass the light, but what happened in depending on the angle of incidence, you would be able to disperse the light to its spectrum. The visible light has a spectrum from red to the violet, yes? So by prism, you would be able, if you change the angle of incidence, you would definitely know that when the light goes through the prism, its velocity decreases, there will be a refraction. If you play with the angle of incidence, you would be able to see the dispersed light, okay? This is what we have in the prism, and we use the prism in the in the cameras, okay? So, and also binocular cameras, and also there are other applications as well. So we have a convex lens, and let me just show all of this here. So I will explain all rules in the simulated screen, okay? So if you are taking, because I'm recording this session, if you would like to take a note, you can take a note right now. If you would like, just listen, because it's being recorded, and you just listen, learn first, and if you would like to practice more, you would be able to watch the recorded session at home. Good? So I would recommend you just listen, okay? So first, again, allphysics.com, I go to the light, and then I start with convex and concave lenses. This is a convex lens, and how the convex lens is created. Let me just explain about the convex lens first, and then we will come back to these here. Okay, so what is this is a convex lens. Oh, okay, how the convex lens is created. So the convex lens, if we have a spherical glass, two spherical glass, which does have a center, and then another spherical glass, good, and again it does have a center, we call this principal line, good. And if you start cutting this part, good, and that part, what is going to be left? The right part, yes? To a spherical glass, good. It does have a center or center of curvature. You cut uncommon area. What you will get a convex lens. So we call this center of curvature. From the center, half of the center for each spherical, it's called focal point, like the convex and concave lenses, sorry, mirrors, okay? And then this is going to be the focal point as well. Good? So the focal distance is the half of radius for a kind of, a sphere. Good? And we know how the convex lens is created. So if we say that this is a convex lens, this is a principal line, okay? This is the focal point. This is the center of curvature. You should know what the focal point, what is the center of curvature is. Okay? What is the focal point? What is the center of curvature? By knowing this, let's just learn about the refractions. Okay, how the refraction happens in the convex lenses and concave lenses. Okay, first we start with convex lens. Go back to this. You don't need this now. Okay. Slide. There you go. Like the mirrors, okay, we just place an object in front of the convex lens. And the lights come and pass through this object. Okay? The reason that we see the object because we receive the light from the object, visible light. That's why we see. The light come and pass from this object, and there are thousands of billions of light. Okay, the light goes from this way, that way, everywhere. Okay, but we just use the 3 incident light. What are those 3 incident light? Let me just erase this. The first one is the light which pass from the top of this. Yes, okay. This is the part of the object that we are trying to see how the image is created, okay, in the convex lens. So the incident light is parallel to the principal line. When pass from this medium, yes, its velocity change. What happened? It will be refracted. And when it's refract, it pass from the focal. This is rule number 1. Good? The angle of incident parallel, the refracted one pass from the focal point. Rule number 2. The angle of incident pass from the center of convex lens without, there will be a refraction inside this area, okay? But, two refraction happen when goes to the lens, when it's come out of the lens, yes? When you do this, okay, you would see that at the end, there will be no refraction, okay? The light just passed through the straight line. There is a refraction inside, okay? But these two refraction, when you combine, you will see that the refracted light it's like the refracted light passing through the convex lens without any refraction. But we know that the refraction happened inside. The combination of these two refraction, okay, make this light pass through the straight without any refraction. Good? This is rule number 2. So again, incident light parallel, refracted light pass from the focal point, incident light pass from the center of curvature without any refraction pass. Good? So the rule number 3, the angle of the incident light pass from the focal point, yes? The refracted light will be parallel. Okay? Number 1, parallel, pass from the focal point, pass from the center without any refraction. Again, we know the refraction happened, but what it appears is there is no refraction. Angle of the incident ray pass from the focal, the refracted line will be parallel to the principal. When I say parallel, it means that parallel to the principal line. What is the principal line? This is the principal line. Good. The intersection of the refracted light will give you the image of that part, this part of the object. Yes, because we were passing the light from this point, we would be able to see that part here. Because it's the intersection happened, with the real refracted light. Good. So the image that will be created is going to be the real image. It is inverted, and the size, okay, the size at this situation, because the object is out of the focal point, the object will be, the image, or the size of the image is going to be less than the size of the object. Good. So you should know how to use these three rules to be able to see the image of the object when you place the object in front of the convex lenses. Okay? Rule number 1, parallel, incident light parallel, pass from the focal, pass from the center without any refraction, pass from the focal is going to be parallel to the principal line, okay, the refracted line. Okay, let's see more examples. So what was the focal point? What is the focal point here? 4, yes? And I place my object at -10. What does it mean? It means that the distance is outside of the center of curvature. If the focal point is 4, what is the center of curvature? Or center is 8. When you place the object at 10, it means that you are placing your object out of the center of curvature. Where is it exactly? If I close this, where exactly, is going to be here. The focal point, let's say, is 4. From here to here is 4. From here to here is 8. Now I place my object here. And I would like to see how the image is created. Good. So F is 4. The object is placed at 10 outside of the center of curvature. Again, using these three light. What happened to the refracted? They intersect, yes? And I would be able to see the image. If I place the object and put it at the center of curvature, what happened? Again, use these three. 1, 2, 3. Intersection happened here. Intersection shows the image of the object. Again, real image, because it's created by the intersection of the refracted light. Inverted, but the size is going to be exactly the same size. The size of the image is going to be exactly the size of the object. If I place the object between the center of curvature and focal point, see, you cannot see, the image here, okay, but there will be intersection. Good. Okay. So, and what is the image? The image is real image, is bigger and inverted. Is still inverted. If you place the object at the focal point, nothing happened. You use that law again, incident, angle of incident, see? Incident light parallel, reflected, pass from the focal, pass from the center. You try to see the intersection. There will be no intersection. You extend the refracted one, yes? There are no intersection. Even the virtual one is not intersecting. What does it mean? It means that there will be no image. But if you place the object, let's say at the focal distance, again, you should use two law, parallel, pass from the focal, pass from the center without any refraction. When you try to connect, you see that the refracted one diverges. What you do, you extend the refracted one. You extend the refracted one, these two, good. You extend these two. You see that the extended one, they will intersect in front of the convex lens. So the image is gonna be virtual. Why virtual? Because it's created by the extension of the refracted light. It is upright, and then the image of the size of the image is bigger than the size of the object. Okay? Again, you need to play with this, okay? And then use that three law that I have explained to be able to see how the image is created in the concave convex lenses. Again, whenever you place the object in the focal distance, we will have a virtual image. At focal point, no image. Between the focal and the center of curvature, real image, inverted, bigger size. At the center of curvature, again, real image, inverted, same size. Outside of the center of curvature, real image, inverted, but the smaller size. Good. How we can see these pictures? By using that three laws. You should learn these three laws. Okay, so let me just make it uh, now we will have a concave lens. What is the concave lens? Concave lens, if I want to explain concave lens, again, like this, let's say we have a kind of rectangle. Good. You will have two sphere. Good. A kind of rectangle cube. And then you will have two, you cut two sphere from this glass. Good. What is gonna left? So if I cut this part and this part, what will be left? It will be this area. Yes? Okay, if I just draw this area, it will be something like this. So again, center, center, F, F. Good? Principal line, focal point, center of curvature, focal point, center of curvature, both sides. Now you know how the concave lens is created. Back to our again, there are three laws, exactly the same laws. Okay, exactly the same law. Okay, I don't want to repeat this slide, but you should know that if the light, I just mentioned here, if the light which pass, it is parallel, if it is parallel, definitely this refract, yes? If you extend the refracted one, it pass from the focal point. If the incident light is parallel, it refract. If you extend the refracted light, it pass from the focal point. This is the number one. Number two. Okay, let me just show you. Number one, okay? So this is the, again, number one. Number two, if the incident light, if you extend the incident light, okay, incident light, and it pass from the focal, the refracted one will be parallel. This is number two. If you extend the incident light and it pass from the focal point, the refracted light will be parallel. And you would be able to extend the refracted light as well. So this is going to be number two. Number three is going to be exactly the same, okay? So number three, if it pass from the center, yes, there will be no refraction. Parallel, refracted, the light will be refracted. If you extend the refracted, pass from the focal point. Incident light pass from the center without any refraction. Incident light, if you extend and if pass from the focal, the refracted light will be parallel, and you would be able to extend the refracted light. Back to here again. Let me just change the focal. Okay, if you change the focal, okay, it will turn from the convex to the concave. So one thing that, it is easy to memorize, the image that concave lenses create are always visual, always upright, and the image size is always smaller than the size of the object. That's it. The image of the concave lenses is always virtual. Why? Because if I place this, you see, if I place in the focal distance, you will still have image, yes? You see the image again is virtual. Why virtual? When you extend the refracted light, they intersect. But the refracted light in the other side of the lens, okay, they never refract, they diverge. But if you extend them, they intersect. That's why we have a virtual image. Okay? So, and if I put in the focal point, again, I still have image. What is the image? Upright, virtual, and smaller size. If I place between the focal point and the center of curvature, it is still virtual, upright, and a smaller size. If I place exactly at the center of curvature, which is going to be 6 point something, okay, again, virtual, upright, and a smaller size, and I put it here, virtual, upright, and a smaller size. Good? But you should know the rule, these three rules that I explained. And you should know how, by following these two refraction of light in the concave lens, you would be able to see the image, which what are the application of these? One of the application of the concave lens is using in telescope and microscope. Sometimes we use combination of two lenses. Sometimes we use combination of lenses and mirrors in a telescope. Let's say this object, good, is a big star which is thousands, billions light year away from the Earth. Okay? By using that telescope, you would be able to see this big size star, which is billions light year away from million light, not billion, million light year away from the Earth, to see its image. Okay, good. And sometime, and then you would be able to see the image of the star. This is one of the application. Okay, so again, we have different telescope. If you are interested, you can study about telescope, microscopes as well. But you should know that in telescope, we always use the concave convex lenses, and combination of concave and convex lenses, and also combination of concave convex and concave and convex mirrors. Okay, so we are done with this, but just one thing is left. Yeah, total internal reflection. So we know that when the velocity, the light is traveling from from a dense material to less dense, okay, from the high refractive to less refractive, there will be a refraction. But we have a critical angle. At that angle, instead of refraction, this borderline between these two medium will act like a mirror. Instead of refracting the light, it will be reflecting light. So again, this happen when the light is traveling from less dense to the, high dense to the less dense, from the less refractive index to the high refractive index. Okay, good. Start from high refractive to less refractive index. So what happened? Instead of refracting, the light will be reflected. Sometimes you are, I don't know, you have noticed that when you are inside of the water, you are not able to see anything outside of the water. So why? Because the angle of the light, the visible light which reaches to your eye is bigger than the critical angle. What is this critical angle? This is the angle if you receive the light from this angle, instead of refraction, instead of seeing the refracted light, okay, you would be able to see the reflected light. What does it mean? It means that you would not be able to see anything. Whatever is outside of the water, you would not be able. Let's say, this fish is inside the water. If the angle of incidence become equal or bigger than the critical angle, so there will be no light reach from the outside of the water. Okay, so this is the total internal reflection. Okay, so we are done with this lecture. Okay, so this was a refraction. We can explain more, but there are I try to explain a little more than your textbook, because sometimes when you are studying a textbook and to see how the images are created in the convex and concave, it's not explained with more details, but I try to explain with details here. But there are good example of application of the refraction, and you would be able to study those by your own, and they are available on your book. Okay, so let me just stop.